Today we're going with the streamer mode. Trying with that. Tell me tell me in the comments if you or just don't tell me. just just don't tell me. What are we doing today? So we are gonna be working on portfolio optimization today. But we are gonna be doing it a bit differently. So I've recently come across a paper. Wait a second, how do I find these? Oh god, this had to pop. What the hell is this? So, how can I find that? So that was a paper from, so that was a message from Sam, the CTO of Multiverse QC, Multiverse Computing, basically. So he, because I tweeted like about like, hey, what's the what's a good overview on on portfolio optimization stuff. Oh, there you go. And so and he basically okay, so that's the preprint about this particular paper, and I think that's worth taking a look at. There's another paper that they shared. I also want to do these, by the way, the Google thing. There's another paper they how this thing is getting the audio right. There's another paper. Yeah, the overview here. So I will also want to do these. Should probably bookmark those because I'm not going to be able to find them soon. So I should probably just, can I bookmark a tweet? I think I got to do these, right? Just add it to bookmarks and then I'll find the thread. So it's basically, so this dynamic portfolio optimization with real data sets using quantum processes and quantum inspired tensor networks. And it's surprisingly quite similar to, or it seems, let me check the PDF if this is the one that I saw. And so here, and the other one was the Quantum Computing for Finance Overview and Prospects. And I've been, I have the impression that this is a really good one to take a look at. Can I download this without paying? I hope so. I hope so. It seems like, because I've downloaded it, I think, but I don't know where it's. Can I just download it so I don't have to? Yeah. So I don't know which one should I do. I kind of can do the overview, or I could also just do this one. I think they're more or less the same length, and I'm interested in these maybe because it's similar to the paper that I'm doing with that I'm tinkering with from Chicago Quantum, where I'm struggling a little bit because I think they just have some gaps in the way they describe how they went through the math, and I just maybe it's worth taking a look at this. It's gonna maybe give me a fresh perspective on that. Something that I can use to kind of reproduce these, maybe, or tinker with that. So maybe I'll do this now, and then next time I'll do the overview, just to kind of background, some core problems in finance, because that can give me some, I think, additional perspective. Some basics in quantum computing, so there's a bit of the basics in here as well. The case for quantum computing in finance. Maybe it might be worth reading this part as well, actually. So the case for quantum computing in finance. Various quantum algorithms offer substantial speedups relative to classical algorithms. This means that when the number of classical bits needed to specify the input data is increased, the number of operations needed to run the quantum algorithm increases slower than the best known classical alternative. In this section, we outline some quantum algorithms which are potentially applicable to financial problems in what follows, and specifies the number of possible inputs aka the size of the problem, which can be codified using log n classical beats. One cannot talk about the great breakthroughs that started the field of quantum computing without mentioning Grover's algorithm, which finds a particular register in an unordered database in square root of n steps. By contrast, the base classical algorithm requires n divided by 2 steps. Okay, so they mention Grover. This algorithm can be adapted to solve optimization problems and also implementing Monte Carlo methods. Really? Grover can be adapted to implement Monte Carlo methods? Grover Monte Carlo methods. Alternatively, the quantum approximate optimization algorithm finds a good solution to an optimization problem in a polynomial time. This requires exponential time on a classical computer. Yeah, so that's basically the variational approach to, I guess, solving the QO, right? Optimization techniques that are also applicable to machine learning algorithms. Indeed, training can be considered a special case of optimization for neural networks. Machine learning also makes frequent use of Fourier transforms. Here again, quantum computers can result in substantial speedups. While classical fast Fourier transforms runs in n times log n steps, the quantum Fourier transform is it's log n squared. Let's consider log n squared. QFT can be useful for some artificial intelligence methods such as quantum principal component analysis and quantum support vector machines. The HHL algorithm for linear systems of equations. Can QFT be used for PCA as well? How? Would you find how? I don't know. Because matrix operations are central to any machine learning algorithm, blah, 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 blah. Okay. But it's interesting that there's no mention of annealing in here, at least in this 2.4. Like, these annealers. Oh, there was something in there. No. What's the first mention in the paper? Simulate annealing. Quantum optimization. Optimization problems are at the core of many financial problems. This is the case, for instance, of portfolio optimization, which we'll discuss in the following. Because it is an NP-hard problem, it is extremely difficult, if not impossible, for classical computers to efficiently determine the best choice of portfolio. There are a number of different ways to implement quantum optimization algorithms on a quantum computer, the most prominent of which is quantum annealing. Okay, so they mention it's the most prominent one. At the heart of the quantum optimization algorithm is a method known as adiabatic quantum computation, which we will describe in the following. First, we must map the optimization problem to the physical problem of finding the ground state of a Hamiltonian, which encodes the cost function to be minimized. We prepare the system in the ground state of an initial Hamiltonian H0 chosen because its ground state is known and easy to prepare, and that's what D-Wave does with the superposition state. We then adiabatically deform H0 to HP over a long time t. The adiabatic theorem states that a system initiated in its ground state will always remain close to its instantaneous ground state, provided its lowest energy levels are non-degenerate and that the evolution is slow. Like, it's awesome because they actually explain the whole core of the thing here just in a sentence, and that's not even explained so easily and clearly in the D-Wave webpage. When this is true, measuring the state of the system at the end of the evolution has a higher probability of returning the ground state of HP, this is a universal method. This is a universal model of quantum computation, which means that it can, in principle, perform any quantum algorithm. That's actually quite nuts, to be honest. Like, how? It's extremely general model as it can be modified to add intermediate Hamiltonians and can be made to fulfill local adiabatic conditions. This process is similar to classical annealing where thermal fluctuations allow the system to jump between different local minima in the energy landscape as the temperature is lowered. In quantum annealing, these jumps during quantum tunneling events, this process explores the landscape of local minima more efficiently, blah, blah, blah. But like, how is quantum annealing universal? How is it a universal model for quantum computation? There's this reference here. This is not, like, this is totally, like, counterintuitive. This is totally counterintuitive to me. But anyway, maybe let's not get too distracted, actually. I should... Is it a long paper? Ooh, 30 pages. Okay, is it basically the concept that you can, like any circuit just can be compiled into an actual Hamiltonian or like into like a unitary matrix, and so you can anneal your way there and then perform measurements. I guess that's why, right? You could, in theory, just like this could be a nice exercise to try. Like, can I turn like for example Grover and like into a matrix and then run it on D-Wave? That would be awesome, actually. Could be something to try. But we are gonna work on these today. Dynamic portfolio optimization with real data sets using quantum processors and quantum-inspired tensor networks. I'm gonna aim at just, for the session now, just as I usually do, fly through the paper. And so kind of, even if I don't understand something, I'll just kind of, go ahead and then see if there's anything interesting that we can do with it. Maybe some sort of comparison with the Chicago quantum one would be interesting. Maybe see if that kind of leads into a cleaner implementation of what they're doing. Maybe they even do it differently, because that's really recent. That's like June 2020. And I see there's people from BBVA in Spanish, BBVA, Madrid, San Sebastian. Cool. In this paper, we tackle the problem of dynamic portfolio optimization, determining the optimal trading trajectory for an investment portfolio of assets over a period of time, taking into account transaction costs and other possible constraints. That's interesting, because the other paper doesn't seem to take that into account. This problem, well known to be NP-hard, is central to quantitative finance. Or maybe they do, but they don't mention that explicitly. After detailed introduction to the problem, we implement a number of quantum and quantum-inspired algorithms on different hardware platforms to solve its discrete formulation using real data from daily prices over 8 years of 52 assets, and do a detailed comparison of the obtained Sharpe ranges. Oh, so they use the Sharpe ranges as well. Profits and computing times. In particular, we implement classical solvers, Gecko, exhaustive, D-Wave hybrid, quantum annealing, 2 different approaches based on variation of quantum eigensolvers on IBM Q, one of them brand new and tailored to the problem. Okay, interesting. 2 different approaches based on... So two different approaches based on VQE. I already know I'm going to learn something, so I'm liking this. And for the first time in this context, also quantum-inspired optimizer based on tensor networks. In order to feed the data into each specific hardware platform, we also consider doing a pre-processing based on clustering of assets. From our comparison, we conclude that D-Wave hybrid and tensor networks are able to handle the largest systems, where we do calculations up to 1,272 fully connected qubits for demonstrative purposes. Finally, we also discuss how to mathematically implement other possible real-life constraints, as well as several ideas to further improve the performance of study methods. The abstract, like, it really makes me feel like that's a dope paper, actually, way more than the Chicago Quantum one. Like, sorry, but it's let's see if it lives up to the expectations. I really want to read through the entire thing. Like, I feel like yeah, that would be cool. So, in quantitative finance, portfolio optimization is the problem of selecting the best distribution of assets that optimizes some objective function. Typically, this objective function tries to maximize the expected returns and minimize the financial risk. The problem gets more complicated if we do it dynamically, optimize the investment portfolio over a series of consecutive trading days. In this dynamic portfolio optimization, the goal is to determine the optimal trading trajectory over the considered period of time. The optimal decisions that should be taken or should have been taken by a broker in order to maximize the overall return at the end of the time period. The dynamic problem is more complex because transaction costs and transactions market impact must be taken into account, as well as other possible constraints. In practice, it is well known that this is an intractable problem that falls into the complexity class NP hard. Parallel to the above, it has been understood recently that quantum and quantum-inspired computing can help in solving hard financial problems. For instance, a quantum computer should be able to solve more efficiently and with more accuracy problems related to pricing of financial derivatives. Okay, prediction of financial crashes, detection of arbitrage cycles, credit scoring, and identification of several types of fraud, among many applications. Portfolio optimization is no exception. Blah blah blah, pre-existing studies. Okay, yeah, none of this work aimed to solve the problem on real data sets, and no comparison has ever been done openly and democratically between different methods and hardware platforms. When was the Chicago quantum paper from? Chicago quantum portfolio optimization. Was this one before? This one. Oh, it's also 2020. Oh, it's July 2020. Wait a second, that was first actually. It's especially similar. July, submitted in July 2020. And that's June 2020, right? Sorry, not this one. This one. It's June 2020. Okay. Let's go ahead. In this paper, we implement several quantum-inspired algorithms for dynamic portfolio optimization and run them for the first time with real data corresponding to daily prices over 8 years of 52 assets. In particular, we implement D-wave hybrid quantum annealing, a variational quantum eigensolver on a quantum processor of IBM Q, a new VQE-inspired algorithm, which we call VQE constraint, also on IBM Q, and a quantum-inspired I lost tensor network, yeah. Optimization algorithm. Cool. We benchmark algorithms using two classical methods, a gecko solver. What is a gecko solver? A Python-based optimization suite. Okay. Let me just check. Let me just check. Oh, why is the chair getting stuck? Oh, no. Machine learning optimization of mixed integer and different. Okay, so this is an actual package. It's an exhaustive solver. We expose how preprocessing is performed and reduce the problem's dimensionality using a clustering algorithm. We then do a detailed comparison of all the results, focusing on the obtained Sharpe ranges and computing times. From our comparison, we conclude that as of today, D-Wave, hybrid, and tensor networks are able to handle the largest systems where the calculations up to blah, blah, blah. Interestingly, we see that there's no clear answer as to which is the best algorithm or how we often deal with large systems, as this depends strongly on different figures of merit. It's organized as follows. The paper section 2 gives an overview of the dynamic portfolio optimization problem. Good section. Oh, we showed how it can be expressed in. Oh, let's do this. Let's jump to section 2. Okay. Let's see if it's easier to understand. The dynamic portfolio optimization problem can be expressed in a form amenable to a quantum computer. In what follows, we present the problem in some technical detail. Where possible, we use the notation of 11. I don't know. technicalities, I guess. Generalities. In the dynamic version of the so-called modern portfolio theory or mean variance analysis, we deal with the issue of allocating weights to a number of assets over a period of time in order to maximize the overall return at the end of the period. More specifically, for n assets, we consider an n-dimensional vector of weights. Like, that's interesting. Like, because here they really keep putting emphasis on the return, like on a given period of time, like towards the future. Whereas in the Chicago quantum paper, I maybe I just didn't read that well, but it didn't seem to be something that was kind of factored into the equation. More specifically, for n assets, we consider an n-dimensional vector of weights, Wt. Each of its component, Wnt, is the weight of asset n at time t. Yeah, so that's actually more. You see, that's in the Chicago quantum paper. They talk about W as being the weights, the assets, like the weights vector, but like they never mentioned like that as like having a time dimension to it as well. So where each of its components is the weight at time t, where Ti and Tf are respectively the initial and the final trading rebalancing times, being the number of trading steps. We also define mu t as its forecast returns at time t, and the sum, or whatever this is, t, the asset's covariance at time t. Mu t is the n-length vector, while this is an n by n matrix. So this is the covariance. I guess the covariance of each asset against all the others, right? Yeah. For a given trading trajectory, a given set of vectors, the overall return is given by. Okay, so the overall return is the sum of the. So this is the asset's forecast return at time t. So yeah, so basically they multiply the forecasted. Okay, the transposed, like, yeah, it's a so the asset's forecast returns times the actual vector with the allocations, and the risk of the trajectory is defined by the sum of, so this was the covariance. So notice that this is the variance of the portfolio return at time t. In practical situations, one typically measures risk at time t in terms of volatility. So if this is the variance, right? If this is variance of the portfolio, and then they just go and say like half the variance. In practical situations, one typically measures risk at time t in terms of volatility. Scrolling. Which is the square root of the variance, of these variance. Nevertheless, equation 2 is a convenient way to quantify the risk in the dynamic setting, since it makes the optimization problem better behaved, being the prefactor half of a convention. The goal of modern portfolio theory is to find the trajectory which maximizes return for a fixed risk. It is common to request a total investment at any given time is. It is common to request a total investment at any given time is fixed, for example, with k the total investment. Let us define at this step the normalized weights. So that's a total investment. How is that total investment though? Time t. with k the total investment. Let us define at the step the normalized weights so that their sum at every step is equal to 1. Ah, okay. I get it. Ah, I get it. So the thing with a stripe, like that's actually not it's not the percentage that you're putting into every asset, but it's the actual investment money. Ah, okay. So then you define that without the hat, like without the line, and that's normalized. Okay, makes sense. So that the sum at every time is equal to 1. So that's basically, yeah. In terms of these normalized weights, the problem can be solved by finding the trajectory which minimizes. Okay, so here they really give like they really go straight ahead like to a Hamiltonian, that it's actually something that's like a cubo friendly thing, right? Um, by analogy to quantum mechanics, we shall refer to the above cost function as a Hamiltonian. This is the risk aversion which tunes the eagerness of the investor to explore risky trajectories, and rho is the Lagrange multiplier that imposes the constraint in equation 3 as a penalty term. We have introduced the n-dimensional vector u with u sub n equals 1 for all n, which makes the constraint more compact. The Lagrange multiplier was fine-tuned in order to satisfy equation 3. Okay, let's try to unpack these. What is it saying here? The equation 5 can also be written as the sum of these h t sub t's, where each h sub t is, yeah, basically the same. It's in here, yeah. Thus the Hamiltonian is diagonal in time. This implies that the optimal trading trajectory is simply the concatenation of the optimal portfolios at each time. No, note that the W sub n, T are interpreted as percentages of the total investment. For instance, having 0.1 means that we invest 10% of our total amount K in the n asset n at time T. Additionally, one may also introduce a cap K prima, K prime, on the maximum amount that can invest in each asset. Okay, we measure the quality of the portfolio by the so-called ratio, Sharpe ratio. This quantifies the amount of return per unit of risk of the trading trajectory. So let's take a look at this for a second, because so mu sub t is the n length vector, is an n length vector. Sorry, mu sub t is the asset's forecast returns at time t. So you're taking the, and you're always multiplying it obviously by WT, which is the vector that encodes the percentages of your investment. And so you take the expected return, then you add, and it's a negative term, right? Because we want this to have, like, why is it negative, right? Like, is it because we want this to be the component that's, like, because we want this to be minimized when I have, want this to be as small as possible. That's what I can come up with, but it's definitely not, like, and then, yeah, and then a plus, and then we're adding, like, so then you're adding the risk component that they define here, where they say the risk is defined like that. I think that's what's substantially different than what the Chicago quantum people do, is it? So notice that, so they take the variance and they divide it by half. So notice that this is the variance of the portfolio return at time t. In practical situations, one typically measures the risk at time t in terms of the volatility. The square, this scrolling is just killing me. The volatility, which is the up again, the square root of this variance. Nevertheless, equation 2 is a convenient way to quantify the risk in the dynamic setting, since it makes the optimization problem better behaved, being the prefactor 1 divided by 2 a convention. Okay. The goal of modern portfolio theory is to find the trajectory. Okay, so they just say that's a convention. It just makes the, what did the Chicago people say? What was that? This one here. So developing the cubo, they go it's page 6 or whatever. So they go through all this stuff and then they so what they do is they, yeah, that's kind of similar to what they're saying, right? The square root of the variance, because there's 2 in here. So what they say is that single asset portfolios will only consider the linear terms in a cubo, in particular where we have a lower triangular matrix. So the linear terms, since your model in the inverse Sharpe ratio on qubits, and there's a penalty on the couplers. But where's the actual Hamiltonian? Is this one here finally? The optimal portfolio. So between the variance of immediately recognizes as the initial formula. So V sub I is the variance, and this is the covariance term between S and Y and J. Y will recognize as the initial formula. And it's not suitable for D wave and its current iteration. We find the Chicago quantum S-score solves this problem and can be presented as a quadratic form. That's what I don't get. Like that's really what I don't get. The Chicago quantum score thing. Like, what is the first place they mentioned these? So here so what they do is they just R sub W is the weighted portfolio. So this is like variance or what, and then alpha is a real number, and we choose an equal weighting. In most experiments, we choose an equal weighting where n is the number of assets included, and we choose alpha near 1. These are not requirements, but they do make the computations in DUI slightly easier. It is a wide open question as to finding optimal weighting and optimal alpha. But they don't explain how to formulate the actual QO, do they? It says CQNS is basically the variance minus the expectation value of your average investment. This makes just no sense. Like, and in chapter 4, they just blah blah about this stuff, and then I guess that is consider universe U of n assets when dealing with a single asset portfolio. We're considering in terms in Q in particular when we have it below a triangular matrix as it products of the form as a peak out on linear terms. If you have two or more assets, then we have more work to do. You look at there's no okay. Blah, blah, blah. We create a unique cube for each size portfolio by applying the weights directly to the matrix. So Qi and Qj can remain binary. We divide the linear terms by n. So they sum up to 1. Yeah, that's kind of... It's a bit confusing because it seems like they don't make a difference between when are the weights normalized or not. We divide the variance terms, the diagonal entries, by n squared times n minus 1 to avoid duplication of what? And divide the covariance terms. Yeah, so they basically use the variance and then the covariance as the off-diagonal entries. So these are the coupler strengths, I guess, to avoid duplication. So I guess they essentially do the same, but they don't compute. Like I don't see where the risk. Like it doesn't seem like they. It doesn't seem like these guys add the risk component to these somehow. Or at least it's not really obvious. What was the embedding part? We embed the CQNS and D-wave by writing the expected returns into the linear terms, both variance and covariance of diagonal into the quadratic terms. Yeah, that's it. That's it. Okay. As we increase our asset size, we see that for fully connected qubit, D-wave requires multiple qubits and chains to leverage the available connections. Then they do some fine-tuning where they don't have links between portfolios that they don't have like a high covariance, because it means that there's not such a difference. Okay, but this makes more sense to me. But how are they going to embed this into a QO? Then it's going to be interesting. But I understand that this is the return on investment, right? Expected return on investment as a minus, because you want to maximize these. Because if you maximize these, then it means that you're minimizing the expectation value of the Hamiltonian. Then you add the risk with a plus, because this means the higher the risk, the lower the return. Like, yeah, you want to minimize. You want to minimize return, maximize. You want to maximize return, minimize risk. So it's got to be a plus term. And what was the U thing here? We have introduced an n-dimensional vector U with U sub n equals 1 for all n, which makes the constraint in equation 3 more compact. I think The Lagrange multiplier rho is fine-tuned to satisfy equation 3. That is interesting. So this seems to be something. This seems to be the component that it's added in there to penalize for portfolios that exceed for choices that might exceed like the total investment we want to have. So instead of limiting the amount of assets you peak, you're limiting for the total amount of investment you want to make, which kind of makes more sense. Because you kind of say, I've got like $500,000 to invest, right? And I don't care whether you peak like 3 or 4, I just don't want you to spend more than that. Like, okay, let's go ahead. We'll probably come back to these. I'm curious about the QO actually, whether they detail that. So okay, they use the Sharpe ratio and not like whatever made up thing. We measure the quality of the portfolio by the so-called Sharpe ratio. I mean, that's maybe it's interesting. So here there's no much discussion about like whether this is something suitable or not. This quantifies the amount of return per unit of risk. Notice that the numerator is the return and not the profit, which would imply removing all the possible additional costs. Suggest transaction cost to be discussed later. Okay, notice also that, for example, on rebalancing step, the denominator is the normalized volatility, understood as the square root of the variance of the normalized returns. Square root of the variance of the normalized returns. That's the volatility. Like I'm gonna have to believe these. I guess I'm not familiar with the field, right? So I really don't know how would you represent volatility otherwise. A large Sharpe ratio means a large return for the risk that is assumed, whereas a ratio close to 0 means the opposite, and a negative ratio means losses instead of profits. Okay. Transaction costs. So how are you going to add these? Okay, so can I jump to the QO somehow? And then I'll come back to this because so this is the simplistic problem, and then they go ahead and they want to add transaction costs. I don't know how they do this, but like I'll go back to this, okay? I'll go back to this. And there's continuous versus discrete formulations. Discrete variables, which is more relevant to big industry players as investment funds typically trade in large discrete amounts. In this section, we will briefly discuss the case where the asset allocation can be approximated by continuous variables. In this section, we will briefly discuss the case where the asset allocation can be approximated by continuous variables. Okay, so that gets probably too complicated. Integrals, blah blah blah. I'll go back to these, I promise. Okay, this is where I wanna get to the QO matrix. I start reading QO here. So discrete asset allocations. In industry, the rebalancing is done at discrete time steps, and it is common for funds to trade assets in large discrete packages. In this setting, the problem is naturally recast as a quadratic unconstrained binary optimization, QBO. For these, we choose a binary encoding of each variable. Okay. So a binary in terms of like whether you invest in there or not, right? For these, we choose a binary encoding of each variable in WNT sub NT in terms of N sub Q. So beats in terms of N sub Q. What is N sub Q? So beats X NT Q. Of NQ, N sub Q beats X NT Q. There are several options for this encoding as discussed example in reference 11, for simplicity in this paper, we choose to work with a binary encoding where the variables can be 0 or 1. By construction, we have that the maximum investment per asset is okay, so it's like you invest in everything. Yeah, that would be like investing in everything, which is naturally included in the formalism. Investments go also in discrete packages of amount 1. Substituting equation 25 into, for example, equation 12 results in a cubic problem for the n total beat variables. Finding the optimal Fourier weights of any given time is therefore equivalent to finding the ground state over the variables x and tq of the classical Hamiltonian. So replacing what it is, so substituting equation 25, so this thing. Into the equation 12 results in, what is equation 12? Oh yeah, that part here. Okay, so yeah, you're replacing it here. Yeah, and then it turns into the cubo thing, right? So you have each variable. Exactly, because you have basically, but why is 2 to the square, 2 to the power of q? Is q the number of assets? Oh no, q is what you're iterating here. Okay. And so that unpacks into what? How is that a vector, though? Okay, meaning like each of these terms would be an element of the vector, yeah. All the variables. Okay. Finding the optimal Fourier weights at any given time is therefore equivalent to find the ground state of the Hamiltonian. The beat vector corresponds to Q matrix, which can easily be derived from equations 12 and 25. Yeah, as I said, it feels like, so it feels like that's kind of what is it, right? Like you're using the returns. You're using the returns as the linear terms, but in T's paper, what do they use as the linear terms? The variance? This variance here? I don't know, it's not clear. To solve this problem on a quantum computer, we quantize equation 26. By promoting the beat variables to qubit operators with eigenstates 0 and 1. Q is the cube matrix, right? Yeah. And that's kind of the expectation value, I guess. That's what it's saying. Or, I don't know. Okay, so here they go ahead and translate it into the Ising spin kind of model thing. where you have the couplings, blah, blah, blah. Okay, that's it basically. And then there's methods overview. So, and this is various methods and hardware implementations to solve the dynamic optimization problem in discrete formulation. These are the following: classical, quantum annealing, quantum universal, and quantum inspired. A D-wave hybrid. Let's go through these. So as is well known, quantum annealing is a type of quantum algorithm based on the ideas of adiabatic quantum computation and is particularly well suited to solve optimization problems. This process is similar to classical simulated annealing, where thermal fluctuations, we know this, Johnson, Miller, and blah, blah, blah. And this is quantum annealing provided by D-Wave, in particular the so-called D-Wave 2000Q processor, which gives access to 2048 non-coherent qubits coupled through a so-called chimera graph. This architecture allows us to solve problems for up to 65 fully connected qubits due to embedding overheads. The D-Wave hybrid algorithm uses the hybrid classical quantum strategy to overcome this limitation, allowing us to deal with much larger problems. In a nutshell, D-Wave hybrid breaks down problems which are larger than the capability of the quantum processor into parts that we combine to produce a solution. Tensor, okay. Then the VQE part, like I want to see if there's some concrete. What is these tensor networks? Data preparation. So I want to dive into the D-Wave ones. I know I said I would go through the whole paper, but I'm curious about the D-Wave details. As a first step, we benchmark our different algorithms, probably using random data. So this is data preparation. The bare return for each asset is given by the price at time t of asset n is p sub n t minus the price and then divided by that price. Okay, so actually they do. So actually I was doing it wrong. I was checking the prices, and I should, like, in by the way, it's in GitHub. I uploaded in GitHub. What? Confirm. Yeah, here you go. So I uploaded it here, and I did this wrong. So I can go ahead and play with it if you want, but like it's really so what I'm just loading is the prices in at close date, I think, and I'm using this to work out the rest, and I should then probably create the returns, which is basically the price you minus the price from the day before, right? From the time before, yeah. Importantly, mathematical expressions often call for logarithmic returns instead of the bare returns. These are defined as these. There are several reasons why logarithmic returns are preferred over the bare returns. In particular, they follow a normal distribution, but most importantly for us, they are time additive, and hence justify the sum in equation 1. In trading situations, though, the bare returns are usually small, implying that bare and logarithmic returns are interchangeable at the expense of a very small error. Okay, that's interesting. There's some dimensional reduction technique. So D-Wave can actually find close to optimal trajectories even with all the problems variables I used. Mean cluster variance, number of clusters. Okay, so what they okay, so I guess what the preprocessing is doing is it's taking the 52 assets and clustering them in 6 buckets, so you have less investment options, you have less variables to play with, right? Is it what they're doing? And I guess they cluster them based on the price evolution. Yeah. Okay. Kind of makes sense. The idea is that they should make it easier for VQE, I guess. Blah, blah, blah. Clustering will also eliminate the noise in the data by applying Prescott smoothing, which extracts the data train. We then compute the Euclidean distance in the data. Okay, so there's a bunch of, I mean, there's some actually decent pre-processing in here, I see. There's some kind of like eliminate, like smoothing the data curve, the data style. Like there's some actual decent stuff done. Turing decrease on basis running average. This has the advantage of eliminating daily fluctuations, which is daily covariance is an estimate of daily fluctuations of a group of assets encoded in the matrix. So once we get an optimal portfolio trajectory for clustered effective assets, we unfold the investment by assuming an equal investment on each asset. Okay, so then what they do is, yeah, they take, so once the algorithm picks an actual cluster, then they assume that you do an equal investment in all the assets in this cluster. Makes sense. Results. Okay, but results like D-wave. Sharpie rate just computed by the different methods. It's funny because in the small problems, VQE is giving you seems to be even like a better solution, does it? Table 1 specifies specifics of different data sets. Okay, so that's what the XS and the XXL. Okay, this is the yeah, these are the okay. So this is the actual amount of combinations. So an excess problem is easily solvable by I mean classically. VQE can't even, like, it's crazy that VQE and even the exhaustive, which is supposed to be the newest this new VQE idea, they just can't like go past S. Like, oh no, that's VQE constrained. Sorry, exhaustive is classical. VQE constrained. Okay, so VQE constrained gets to the size M, but it's still like it really. You can really see the D, like already with size S, like the D wave and the tensor networks just go over the roof in terms of their Sharpie ratio. Like that's way better, 8.9 than like 6.04. It seems like for XXL, like really the tensor networks are winning. Actually, tensor networks win already from step M, from size M. That's interesting. Okay, but so these are the results being discussed, which we can go through later. Next steps. Okay, so here how to make constraints. Market impact. Intuitively, when a large order is passed, it can affect the market. For instance, a large buy order may increase the price of an asset because it signals high demand, whereas a large sell may decrease. This is, of course, would alter the optimal trading trajectory. As discussed in reference 11, this can be implemented with market impact coefficients. So they add another piece of data in there. For escape, blah blah. This is like, this is really detailed. Okay, so I do wanna, I do wanna end up like running these like on the D-Wave stuff, like, and just using the data set that I have. Okay, so I gotta probably correct some things. I definitely gotta correct the returns, and what these really seems to indicate is that like the cubo is basically the returns. The expected return is the expected return is basically the a linear term, but they also add another linear term in here, which is the risk, right? As a sort of a penalty. And then there's penalties. Where was the, what was the equation? Was it equation 25? No, it was equation 12. 12. Here it is. So you have the expected returns, and then you have, yeah, there you go. Yeah, then you have the, so does this mean the transpose? Let's figure this out. Like I think that's a transpose. What is the risk? So this is the risk. The risk of each investment. Is they multiply the investment by this, which was the covariance. So it is actually covariance, but it's half of the covariance. So here they use the covariance as well. But then what is the other? What is these part? This is the Coherence Matrix, right? I guess that just means these in column form. Because if that's a matrix, that would, yeah. Mm. The variance of the portfolio. Return. Matrix. So where is this defined here? So this is the assets covariance. Although covariance with what? With the market? Maybe that's the assets covariance with the market. Mm. And so what they do here is this was the return minus the return free, the risk-free return. Those things might be quite equivalent. But they use the variance and the covariance term between assets I and J. So I'm not so sure. I think it's a bit different because I think that is a risk, like it's an isolated risk. I think that's the isolated risk. I think that's the isolated risk, like comparing, sort of it's the covariance with the market. So that's the volatility of the asset in isolation. And then these other component here, what is this other component here? So the Lagrange multiplier, okay, let's see. It's fine-tuned to satisfy equation 3. Okay, but what is it there? That's just the constraint. That's the constraint on the maximum investment. So okay, let's see. Let's think through these. I feel I'm just reading and not like thinking, you know. So forget about the square part. That's just to make that just like a bigger constraint. So rho is a Lagrange multiplier that imposes the constraint in equation 3. What is a Lagrange multiplier, first of all? Why they call it this way? So this is supposed to impose these. So basically what it does is, so an UT is, where U sub n equals 1. So what this does is it takes it basically I don't know actually how like it's not obvious what are the quadratic terms in here, to be honest. So what are the quadratic terms? are the ones with the couplers. In the cubo, the off diagonal are the. So what is these first of all? What is a Lagrange multiplier? So in mathematical optimization, the method of Lagrange multipliers is a strategy for finding the local maximum and minimum of a function subject to equality constraints. It is named after Joseph Louis Lagrange. The basic idea is to convert a constraint problem into a form such that the derivative test of an unconstrained problem can still be applied. The method can be summarized as follows. In order to find the maximum or minimum of a function subject to the equality constraint gx equals 0 form, the Lagrangian function x lambda equals f of x minus lambda times gx. What's the subtle point of a Lagrangian function? What? So the great advantage of this method is that it allows the optimization to be solved without explicit parameterization in terms of the constraints. What the heck is this? What is a Lagrange multiplier? So let f be the objective function, g be the constraints function, both belonging to C. Let every optimal solution for the following optimization problem. Maximize f subject to g equals x, gx equals 0. So this is the constraints that you have. Then there exist unique Lagrange multipliers such that whatever d times f. The Lagrange multiplier theorem states that at any local maxima or minima of the function evaluated under the equality constraints, if constraint qualifications apply, then the gradient of the function at that point can be expressed as a linear combination of the gradients of the constraints at that point. I don't know what is this. So okay, but this is, so then I guess this is something that is pre-computed for this constraint that that ensures that, like, intuitively speaking, what this is doing is somewhat like, so it's trying to enforce that the total sum of investment is K, is capital K, and that's the point, is like that the approach here in comparison to the Chicago quantum one is that you're constraining on the total amount of investment. Yeah, but that's equivalent, right? Because if you're just normalizing it, so the size of the portfolio you're picking is really dictating the total amount of investment you make. Yeah. But it feels like it's better explained here. But still, it's not clear what the quadratic terms are for the cubo. Cubo. Substituting equation 25 into equation 12 results in a cubo problem for the n total n times nt times nq. So you're replacing the saying that WNT is basically the sum of these. Okay, so I guess, yeah. I guess what makes that the quadratic term is the fact that when you square these, then you're going to have the actual variables being multiplied to each other. So once you replace these in here, you're going to have, it's the same like these times the same, and so this is when you're going to have like the variables multiplied by each other. Oh, sorry, not here. Is it here? Yeah, actually it's here. What is these though? When did I miss that? Oh, that actually... For instance, having... Additionally, one may also introduce the cap K prime on the maximum amount that can be invested for each asset. The two quadratic terms. Ah, that's the transactional costs. Discuss both. Okay. Yeah, I think this paper helped me sort of, I think, walk through the problem better than the Chicago quantum one. I have the feeling the Q seems to be the same or similar, but this one, so there's something that constrains based on this Lagrange thing, which I don't really understand. It adds this, so it's way more detailed, like the transactional costs. It has a thing, a bit of a different conception of concept of risk, and then it's using the expected return as the linear component, whereas in here it seems to be using the variance, I guess. If this is really what goes into the cubo, right? Because they don't talk about these at all. They say the linear terms by n and apply the linear affine transformation. The variance terms to avoid duplication, whatever that means. Reverse the sign on the linear terms. Finally, we apply a scale factor to the cube and write it into a matrix for participant D-wave. When exploring portfolios of different sizes, we present a different matrix to D-wave for each desired size portfolio. We add a penalty for exploring portfolios of different sizes while maintaining accurate values for the desired portfolio size. The intuition for this follows closely from converting a cubo into an Ising model. In order to convert a cubo into an Ising model, we consider the transformation on the binary vector x. Since we're only looking for the location of the lowest energy, there's a criminal to convert back to x and find the actual lowest energy. Thus, our intuition leads to consider affine transformations in x. Our goal at this point is to find a shift which we can apply to the quadratic form. This corresponds to translation, and is this closely related to the term above. In our formulation, we do not use balance, although our mathematics takes it into consideration. In this case, balance will correspond to a boost in our coordinate system. Given the universe U of assets from which to choose, we define a shift factor Sn for exactly n bigger than 1 assets from U, which is the best score derived from a classical simulation. In this case, a genetic algorithm is a multiplier. Empirically, our multiplier m is generally around 5. Intuitively, errors can be multiplicative, and so we can say values close to to linear terms. There's some sort of shift added. To quadratic terms, there's another shift added. Covariance features of the market and beta based on log returns. Covariance seems to be assets. We've done all these. Derive a Q for each portfolio size. Like, I don't get why they need to add these shifts. And why they have a specific Q for each portfolio size. That's kind of... in the results, like, do we have some kind of... maybe references, maybe they have some code somewhere available. Outlook. It's overall like a... this paper feels really decent in comparison to the other one. And so the differences are here. I'm trying to understand why. So why did the Chicago quantum people need to apply the shift somehow? Why do they need to have a Q that's different for each portfolio size? Whereas maybe there's something hidden in this Lagrange part of things here. That's kind of where I don't really understand. And then here they study market impact and stuff like that, Lagrange multiplier. It seems a much more compact way of doing that. Hmm. Hmm. It's nevertheless. So here they talk about, again, they they talk about the constantly talk about K as the investment limit, versus in the other paper they talk about N as in like the number of assets that you want to invest in, which seem to be, I mean, they must be related, right? Especially, no, they don't have to be necessarily related, right? Because you can just invest everything in one asset. So I think these, if I'm getting these right, like that is better, because it's not limiting you in terms of the number of assets you wanna invest in. It's limiting you in terms of the amount you want to invest in. Mm, but like the optimal, like the result that it's picked, like can be, really stretched, or it can be just really compressed into like just one or two assets. That's the feeling that I have, and I think it kind of makes a bit more sense. That's what we try to limit. So that's this Lagrange thing here. So the Lagrange multiplier, which so single constraint examples. So suppose we wish to maximize x plus y subject to the constraint that x squared plus y squared is 1. In our case, like you want to minimize a function that's your cubic function with a constraint that it like all adds up. No, okay, with a constraint that like yeah. With that constraint, the k thing, right? Like that the sum is like it equals k. The feasible set is the unit circle, and the level set of f are diagonal lines of slope -1. I have no idea what they're talking about. Okay, so they're basically the minimum occurs in this point. For the method of Lagrange multipliers, the constraint is gxy. Gxy would basically be, okay, so you have to come up with a gxy, the g function that equals 0. So you kind of pass, like move the 1 there, and hence the Lagrange. What Lagrange is saying is that there is then this f of xy plus like this lambda times the g function. Now we can calculate the gradient. Okay, so you do the gradient of these, the derivative, right? So you do the derivative of these, and then you end up with the systems of equations. And now notice that the last equation is the original constraint. The first two equations yield that x equals y equals -1 divided by 2 times lambda. Lambda cannot be 0. And by replacing these into the last equation, then we have that lambda is plus minus 1 over the square root of 2, which implies that the stationary points of L are these. Evaluating the objective function f at these points yields square root of 2 and minus square root of 2. Thus the constraint maximum is square root of 2 and the constraint minimum is minus square root of 2. So you're taking the constraint. So what are you doing? You're trying to... okay, so but what's the essence of these here? The f plus that. That's... kind of, I get the process in here, but like what was it saying? The method can be summarized as follows. In order to find a maximum and minimum of function f subject to the equality constraint, So fx minus gx. So this is a constraint. And find the stationary points of L considered as a function of x in the Lagrange multiplier. The solution corresponding to the original constraint optimization is always a saddle point of a Lagrangian function, which can be identified among the stationary points of the Lagrangian function. A constraint, which is called Lagrange multiplier. It's very important because it measures the change that occurs in the variable being optimized given a one-unit change in the constraint. So okay, so this we'll dive into these in the next sessions. I don't know how long it's how long we're going to be working on this, but so what this Lagrange multiplier is measuring the so it's somewhat related to to that constraint, but that constraint applied to the function of what? The function of kind of calculating the returns, or so you have a function that is basically, in this case, what's the function? Like, what's f of x? Like, what's the function here for calculating the Lagrangian? Like, that's what I'm missing. But I guess you just have to read that maybe when it's not that late, and maybe, you know, not 1 hour and a half into the whole thing. Okay, but it's something that's then related to that constraint. I get that, and we use this as a penalty. Mm-hmm. Why does this work though? Like, why does this really enforce that, like, why does this really, I still, okay, so the question that I have to answer here is how can these really enforce that constraint that we don't go over k, or that, like, especially when wt is normalized, right? So this is basically so w sub nt is ds divided by k. So it's the relative investment already. It's the percentage investment. And this u sub n equals 1 for all n. Which makes the constraint in equation 3 more compact. It's the combination of this ut and this rho what, like, enforce this constraint. But this is not, like, I'm not entirely sure how can this really guarantee. I guess this means you're. So I guess this means if if you're gonna have a solution, if you're gonna have a solution that goes over that, right, then you're basically you know, that should give you a bigger number. So those are being penalized. But like, how does this ensure that you really invest k, like that it equals k? That's what I don't really understand. It's like, how does this work? That it actually ensures the investment equals up to 1. It doesn't peak like small, like a smaller portfolio with like a less investment. That's what I don't really understand here. That's the only thing. Like, how does the constraint is really enforced? Okay, yeah, maybe, you know, I really want to actually try to run a Cubo. Yeah, cool. That was fun. That was definitely fun. Yeah, if you're liking these videos, I mean, probably nobody's watching by now already, but if you're liking that and you want to subscribe to the channel, you're going to make me, you know, really happy. I enjoy a lot seeing that people like the content, seeing that people want to subscribe to, you know, be notified of more videos coming up. But I'm going to be uploading more often in the in the near future. So stay tuned for these. I'm really enjoying that. You know, digging a bit into the quantum annealing part, it's also fun, and sort of like taking a look at the financial stuff. It's just, I mean, you can just get so easily lost in here. But I want to take a look at VQE, the VQ constraint part. But I really wanna get the D-Wave stuff done. I just wanna run one example somewhat. But I'm feeling really lost. I'm feeling really like I don't know kind of what the next step is. So what I have is I gotta fix that to calculate the actual returns. And now I would really have to build the cubo, right? Like, that's kind of the next thing that I want to do. And to build the cubo, I guess I just have to take the returns, and those are the diagonal terms minus. I gotta add the risk, though. To these, right? Minus the return plus the risk, but that's the diagonal terms. And I want to calculate this stuff. Like, what are these off diagonal terms? Like, how do we calculate these? Like, what's the actual problem for blah blah blah? Find the optimal portfolio weights and making times, therefore going to find the ground state over the variables, the V vector, and Q being the Cubo matrix, which can be easily derived from equations 12 and 25. So the keys are in equations 12 and 25. 12 being this part in here, and 25. So this is what I want to really focus on. 25 is this, which is kind of basically, yeah, we'll try to figure this out, okay? So next time we're really getting into the actual coding, and then, you know, what we can do is, actually, I'll try to compare both cubos, like this one and the one from the Chicago Quantum guys, see if there's any difference. Like, I don't really remember. This cubo has the shift stuff, man. Like, I'll definitely. I want to really get this done. So this has the shift things that I need to figure out, and the other one, it's got this Lagrange stuff. So those are the next big challenges. Cool.